my notes for it. So part of the motivation for this is so that I feel like I have to have read my notes before I come to this call. Otherwise, so it's motivation for me to get through these papers. This is a big part of this, and I've been trying to take more deliberate notes on the papers I read because it's just so easy to gloss over a paper and be like, oh yeah, oh yeah, oh yeah, and then I'm just wait, what was that about? So that's another aspect of it. But yeah, I'm happy, Chris, to have recorded however if you are Paul.
Cool.
It's fine with me
Yeah, I have
and
no problem.
Okay. Cool.
um
I'll start
like
recording in a sec. But yeah,
yeah.
feel free to continue,
Um
Fraser.
would did would we want to go through the paper, or do we like did people manage to get through the program paradigms one because it was hefty? So if you didn't, then there's absolutely no trouble.
Yeah, no problem at
Um,
all.
and there's also I also found that it jumped all over the place because it was sort of like a condensed version of his book. It wasn't really centering on any one particular thing. Like it was paradigms, but then it was jumping around from what a concept is to what the perfect language would look like in sort of variously in a bit of a jumpy way. Um, I'm very glad you picked that because I've followed him along for a while. So Peter and Roy he's got a book on the same topic, and he publishes his lecture series from the University Lectures app online, and he runs like an advanced programming paradigm course. So I've been meaning to get through the videos for a while, and I've got through some of them. But it's good motivation to actually. And I really think you could start with that diagram he has of the programming paradigms, that big one where he maps the concepts onto basically how you get from paradigm to paradigm by adding concepts. So I think it's just such an interesting diagram, an interesting way of framing how languages can be grouped together and how the paradigms that they express are related. Um, so do you have that
I could
somewhere,
share it.
Chris?
Yeah. Yeah,
Yeah.
shared. Yeah, overall, just like my comment, the diagrams in this paper were fantastic. Um, Absolutely loved them, and it was consistent as well. But it is funny. I feel like we had like 35 pages of talking about paradigms, but I also don't feel like he ever defined what a paradigm is. It felt like we were, in my opinion, and maybe I missed, the part where he defined it. It felt like we were pointing at something, but we didn't have the words to describe it, which I find funny. I don't know if you and I think concepts were sort of like here's a bunch of at least in this paper. Maybe the book's different, but I haven't read the book. Concepts are sort of like here's maybe not a definition of a concept, but here's a bunch of different examples of what I mean by concept, and maybe we could form a gist of what that means. But I think there's such an interesting the reason why I picked this topic and the two main papers that we're talking about, notation as a tool for thought and this intro to paradigms, is I think there's actually a lot of overlap between them. Paradigms feels like a more computational kind of uh, lens on it, but I also just think this concept of like making notation, whether it's mathematical or some kind of visual notation, I think there's a lot of overlap between it because I think they fundamentally like affect how we think and reason about programs, sort of what we don't have to think about, what we have to think about. Um, and so yeah, that's why I sort of just the short background on like why I thought these different concepts are like related and sort of what I'm interested in. Uh, so yeah.
Yeah,
Well, sorry, Paul, you go.
I was confused by the difference between concepts and paradigms. And then I found a slide deck on one of his web pages that started to unwind that, but then I didn't have time to finish going through the slide deck.
Yeah.
But I think he misses a very fundamental question that appears to be assumed by everyone, that a programming language, the question is, who is the programming language intended for? Is it intended for human readability or machine readability? And I think there's very few programming languages aimed at machine readability. But if you do that, you open up a Pandora's box of possibilities for automation. And I believe, I don't write programs, I write programs that write programs. And that's what a Lisper does, and that's what a compiler writer does. Um, and the concerns with respect to choosing syntax for humans versus choosing syntax for machines are different, very different.
Interesting. And is it always the case that is it a trade-off against each other? Like if you increase computer readability, you're always decreasing human readability, or is that not the case?
Um, I don't know. I know that if I laser focus on machine readability, I don't care how human readable it is. I keep it in ASCII or Unicode or something so that I can dig through it to debug it. And it is quote unquote human readable, but it's not conveniently human readable. Um, So, one of the way I look at Lisp these days is that it's actually assembler, but it's assembler with a recursive syntax. Whereas the thing we call assembler is assembler with a line-oriented syntax. And those are the basic principle differences between the two. Basically, a Lisp is, common Lisp is just a bag of functionality. And because it has a recursive syntax, it makes it easier to compile text to that using whatever text tools recursive descent text tools. CFGs don't promote that type of thinking, but recursive descent does. So OhmJS, PEG related parsing expression grammars um, encourage that kind of thinking. So there's little languages that you can pepper at humans, but there's also hundreds more of little languages that you could use to facilitate machine automation. So I see it as, of the syntaxes, I think 10% of them are for humans and 90% of them should be for machines. And when I learned how to do compilers, it was, you can draw a box diagram of a compiler, right? A scanner, a parser, a semantic analysis, blah, 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 allocator, emitter, and so on. But I was taught we used a tool called syntax semantic language. It was spelled SSL, which means something different these days. But it was a recursive descent parsing language, like say Ohm, and it made it easy to think of. So what syntax would make it easier to do this task? Type checking. What syntax would make it easier to do allocation? And the answers are different. And so you pipe these things together and you threw away noise and you added information. And by the time you got to the other end, there's nothing, it's completely typeless by the time you get to the emitter, and you just emit it because the other passes did their job, and if it got to that, then it's okay. Where but I wouldn't call any of those intermediate little languages human readable. You can read them, but they're not convenient.
Would you say then, Paul, that you feel there's a lot of effort going into the wrong space? Because to me, it feels like the push is to make language is more human readable or make more human readable language. Maybe I'm wrong with that. And that could be sort of the ecosystem I'm in as well. That it feels like that. But if you're saying that you'd say 90% of languages should be for machines, do you think the effort is not going in the right place, or sort of we're looking in the wrong places?
Well, I think we're just cutting off a, an avenue of thinking.
Mm.
And I believe very strongly in automating things. So I wrote a lot of bash scripts and that sort of thing. But doing syntax directed translation makes the job of writing a compiler a lot easier and makes a whole pile of other things easier if you think about it that way. Whereas I perceive at the moment what we've got is this wodge of human readable languages, which should be human readable, because making a language human readable allows the human to think about more abstract concepts better. And so, in essence, that's what a chip is, right? I learned electronics, so I can draw you a schematic, but getting over 100 transistors on a schematic, it starts to become mind-blowing. So you invent some sort of little language that says, so I'll arrange these transistors to do this particular task, and here's the little language you get to invoke bits of that task. It's more like an API, but but if you couch it as a language, I'm not sure that I'm answering your question. So I think the question was, do I favor machine readable languages over human readable languages? And the answer is no. You need both. But I think the idea of machine readable languages has been ignored in lieu of making all languages human readable. And human readable languages are way harder to compile, to automate than machine readable languages. And, sort of the last language that did both was Lisp. And a lot of people hate Lisp because it's machine readable. But that's where you got macros from. And the whole point of macros in Lisp is to write scripts that bolt pieces of code together in ways that you don't want to have to think about more than once
Do
or ever.
do you think I'm just one question about this distinction? Do you think paradigms apply to machine readable languages, like as von Neumann sort of tries to define them, or is it a sort of like are paradigms a facade at the machine
Um,
level?
I've written somewhere that paradigms are the important thing, but like the Roy paper, Roy, yeah,
Yeah.
I fail to define what I mean by the word paradigm. um, uh,
I I have a definition that was in the paper, but I'm not sure it clarifies anything. Is programming paradigm is an approach to programming a computer based on a mathematical theory or a coherent set of principles. What I guess it's really sort of a giving a name to a certain collection of concepts is what it seems to be. Like the relationship is a paradigm has some concepts, and maybe there's also some concepts, and you give it either emergent properties or a certain flavor to them that makes them, something we can name. Um, but I think it's a struggle when you sort of try and decompose things that are already sort of familiar. For example, like object object oriented programming. It's a very overloaded word. When you decompose it, but then still try and use that label against your decomposition, it can be a bit of a mismatch, I think. Um, It almost feels like concepts are more of the
Oh, we lost you.
Yeah.
Okay, coming back. I also have. I wouldn't say it's a definition of paradigm, but pulling from the little language, writing on little languages. I'll quote it when Fraser comes back. But I think it's more of a framing than a definition about what a paradigm is. Um, but yeah, it feels like this very elusive thing, and I
Sorry,
I
my
don't like
headphones
that.
started to die.
Oh, okay, cool. Yeah, we could hear you again.
Are you getting any feedback? Like when you cross talk, Chris, are you getting any feedback?
I think you're good.
Okay, cool. Yeah, sorry, I was just saying, I think it's almost concepts are more of the not innovation, but the interesting way of thinking about the languages. And paradigms sort of are the bucket that you have to put concepts in. But like, for example, in the diagram I shared, I think it's a really interesting framing to me the way that you can go from paradigm to paradigm by adding a concept in this framing. Um, and how sort of is trees to these you can add a closure to a procedure and then you've got functional programming, or you can add a closure and a cell to something and you get, it's just a really, to me, a very interesting way of bucketing and yeah, interesting decomposition. Um, 'Cause, yeah, often I think the way things are presented, people talk about them like it's functional programming versus object-oriented programming is just pretty much wrong. It's not a correct framing. And I think something in a diagram like this makes it a bit more clear, like how you could think about them in relationship to each other. Um, but
um,
yeah, there's what is sort of one part of what he talks about. But I think the concepts, that decomposition is what I was interested in. Yeah.
um, what you guys are saying reminds me of the one thing I learned in physics was to apply simplifying assumptions.
Mm.
So if you and how to figure out if something can be applied. So a simplifying assumption is one that throws away details but proves that the details are so insignificant that you can throw them away
Mm.
or ignore them. And the point of that is that if you can compress um, the the notation down, then you can use the notation to think about bigger things. So don't know if that was the right wording, um, but well, the example of electronics. So if I drew you a schematic of something versus giving you a CPU with a fixed API of 80 instructions as opcodes,
Mm-hmm.
you 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 can do more things on top of those 80 instructions than you could with my schematic. And that goes all the way down to atoms. That's why we have, atoms break down into something else. And that above atoms is molecules, and above molecules is, and electronics is just dealing with rust and electrons passing through rust, um, oxides, chemistry, stuff like that. So to me, important paradigms are the ones that reduce the amount of the work that you have to do and allow you to spend more time thinking. So garbage collection would fall into that category. Object oriented would fall into that category. Prologue falls into that category. It's one of the things you do in, I think of programming, there's only two things you do in programming. You inhale and then you exhale. And the
Mm-hmm.
inhale portion Prolog is one of the tools that does a nice job there, trying to understand what you've got. Parsing, inferring, etc. Getting information out of things is easy to express in Prolog. It all comes down to assembler anyway. So you can always write it out in full if you want. And so the trick is to find a way to compress down the number of things that you have to say to get the same effect. That to me is a paradigm. Um, and then the other thing to me is a syntax. So I say syntax is cheap, paradigms are important. So so the idea is you have a toolbox full of paradigms, and that toolbox is usually not very easy for humans to use. Systems programmers fool with them, but normal humans find it to be way too cluttered with detail. And so you skin it with a syntax that helps them do their job and draws on the tools that are in the toolbox. And then you throw it away, or you ignore it and you give someone else a different syntax. And so the problem has been, how do you whip up syntaxes? And up until Peg came around, um, whipping up syntaxes was not front and center in people's minds. You used things like YAC and CFGs and that sort of thing, and it was a laborious task. You're inventing language was, oh, well, that's a couple of months' work, easy for starters, and then probably a year by the time I finished debugging it. Whereas whipping up a syntax in Ohm is 10 minutes, especially with the Ohm editor.
Yeah.
So if it changes the way you think, to have the freedom to say, I can invent the syntax for this. So I've got this 1,000-page legal document called the Common Lisp Hyperspec, which, after decades of using it, I still haven't memorized it. I still have to pull it up all the time. Same with Emacs. But where was I going with that? So I've known for a long time that I could use recursive descent to create little languages on top of that. But now with Peg and OhmJS especially, I just whip them off. And to my detriment, I'm a lousy estimator of time. So, I usually think I can get this done in the next 10 minutes. And then, 3 days later, I keep going down rabbit holes and stuff. But,
I guess a question that is about what you just said, Paul, like, what is the relation? I'm interested in the relationship between syntax, such as you're talking about, and being able to sort of generate syntaxes, and whether you're actually able to add new concepts in the way sort of Roy is talking about, or how a syntax relates to a concept. So, for example, adding a cell or named state into, like, that seems like something that your language either has that or it doesn't. And but maybe some of these other, when you think of a paradigm, like he does talk about the creative extension principle. The question is, how do you generate a bag of concepts and make it a paradigm? And what he talks about as well, if you're trying to solve a problem and there's lots of sort of incidental complexity in solving the problem that's arising from the language itself, then that's a sign that perhaps a new concept would help actually simplify the program or the way of writing the program. And that almost seems like what you're talking about with syntaxes, but I'm struggling to see how you could add concepts via syntax itself. But maybe you can. I'm not sure if you have any thoughts on that.
the way I see it is you don't add syntaxes that way.
Right.
You don't add concepts that way. So you have a toolbox full of concepts, and people are arriving at them, um, and saying, "Oh, here's a good way to think about this kind of problem," and you just throw it into your toolbox. Um, and the syntax business is how do you make those things accessible to a wider range of people?
Mm.
So, offhand, I don't think you come up with, although historically that's what's happened. I mean, like object oriented was invented by, basically, let's say small talk. Um, so it came with a syntax that supported the ideas of object orientedness.
Hmm.
Functional programming probably is that way too. If I worked at it, garbage collection was one of those big steps forward. That everything was done in assembler and C, and you called malloc and free, and you would tangle things up and so on, and then a garbage collector just basically all the code that you wrote for it untangled all your code to not have to think about that stuff. You just said, here's X, I'm using X, and someone will garbage collect it for me. And it turns out, in my mind, garbage collection is a waste of time anyway these days, because we can afford memory now, whereas in 1950 you couldn't afford memory.
Mm.
So all these considerations that go into languages are based on 1950s thinking instead of 2024 thinking. You know, I can afford, if I take away multi-threading, a whole pile of problems go away. Um, so can I take away multi-threading? Well, yeah, just, buy another Arduino. $5 here, $5 there, who cares? You know.
Although you and Von Roy share a distaste for multi-thread. Uh, he's very for the declarative concurrent languages. Something I've come across a lot actually. The synchronous languages are all about avoiding having concurrency and determinism at the same time, and basically you do that by not by running it sequentially. And there's only concurrency at the notation level.
Yeah.
Uh,
So just to pile on here, and I think one of the other papers that was in this group was Iverson's notation as a tool for thought, and I think he has a very short list of things that like are important to a mathematical notation or computational notation, and ease of expressing is an important aspect. It was the first aspect, so I note that as probably the most important thing for him, sort of as Paul was alluding to. The ability to subordinate detail was another one up on that list. So the ability to sort of hide away complexity. I don't know if I'd call it abstraction, but maybe I don't know. A lot of these terms that we use are just so overloaded nowadays. It's really hard to pinpoint them. But when Fraser dropped off, I said I had a framing of what a paradigm is, and I think Paul alluded to it as well. It's a quote from this book called "Constructing Language Processors for Little Languages" by Randy Kaplan, and the quote is this: all programming languages are based on paradigms. For example, the Prolog language is based on the paradigm of logic. Smalltalk is based on the paradigm of objects and messages. IL is based on the paradigm of events. These paradigms cause languages to be extremely powerful. Programmers not need to be concerned with explicitly implementing the underlying paradigm of any language. The fact becomes particularly important when that paradigm is complex. The paradigm, in a sense, is the ability is available to the programmer for free. So it's the framing of like what the paradigm is what what do I get for free if I'm using this programming language? What don't I have to think about? Which then allows me to change my focus. And so part of that, I think, is about conciseness and syntax. Like, how easy is it to concisely articulate these things? That I think that's part of what of how you get something for like a paradigm for free. Then the other part is like, how is this changing how I'm thinking about or what I need to focus on? I think those would be the two parts that I would sort of say. I don't know. I'm still pointing out what a paradigm is, but that's maybe helpful, helpful here. Yeah.
Yeah. I mean, what you said, I agree with. Yet, if you held my feet to the fire, I probably still couldn't define what a paradigm was. The words simplifying assumption make more sense to me, but maybe because I came up through physics. And the guy I lean on is Richard Feynman. I mean, he was steeped in, we got to define physics using mathematical notation, and yet he stopped doing it for a little while, drew diagrams, Feynman diagrams, and figured out something that people couldn't figure out, or couldn't analyze, couldn't describe, couldn't deep dive into until he did it using diagrams. And it's kind of the same thing that's going on now. I mean, let's pick on garbage collection. So without garbage collection, you're mired in a pile of details for handling memory. With garbage collection, you can think about things. You can waste those brain cells on thinking about something else. And that to me is what a simplifying assumption is.
Yeah. And one of the questions that I had reading this paper was, so you're talking about how creating this new visual notation helped him think through those physics problems. Does visual programming unlock a new set of concepts and paradigms that we have access to that we can't express in textual form? I think that's one of the questions that I had about this. Is the map and the taxonomy of the paradigm of the programming paradigms that Van Roy sort of outlines, is that trapped in a textual syntax?
I think the lowest hanging fruit for handling with non-text is concurrency, asynchronous operation of things. So having developed schematics in the past successfully, more successfully than developing software for decades, all of the elements on a schematic are completely asynchronous. And I think that talk about an asynchronous, truly asynchronous, free will thing, you need to be able to discuss things that run at whatever speed they want to run at. They can accept inputs, and they're not forced to produce outputs until they're ready to do so. Or, that's like Unix daemons and stuff like that. And I have not seen a good textual notation for that, for expressing that. Whereas everyone knows what a graphical notation for that is. You just walk up to a whiteboard, you draw a box, and you put a bunch of ports on it.
Yeah.
And some lines between the boxes. And back to the paradigm or simplifying assumption thing, I try to call it build and forget. So building something and knowing that it will never be affected by something else is important to me. It means I don't have to worry about that aspect ever again of programming. Whereas using our current languages, you never know if something is going to break because they're so internally coupled that a change here causes a spooky effect somewhere else,
Mm.
and a breakdown somewhere else. And, that's dependency. So getting rid of dependencies, but truly getting rid of dependencies, not just data dependencies, but control flow dependencies, can deliver uh, build and forgetness to you. And when you achieve build and forget, then you are freed up to use your brain cells to deal with even more interesting concepts, like whipping up little languages, uh, orders of magnitude faster than what we think one should be allowed to
Mm.
do. Um, I don't know. Was that
Yeah,
was
no.
that clear? Okay, sorry.
I mean, I'd say, coming back to the paradigm and what paradigm is, I think you could almost answer the question by like what was important to know about a language when when Roy defines two purposes for the paper. One is for if you're a programmer and you want to know what language to use to solve the problem you're working on. Then also if you're a language designer, so that you can think about like what you might want to include in a language, because you need to choose what your language is going to support. And I think we've spoken about it, that really it comes down to sort of what is made easy, what is made concise, and what affordances are provided to the developer through the notation that speaks to sort of what the paradigms are doing. You can also think about maybe like how would you decide if a language is in the same family of things? Like what if you go past the name of it, like what makes these two languages really similar? And it's sort of like it's almost definition by negative definition, right? It's not that there's a word for it, but you can sort of see like if you didn't have paradigms, like how do you even compare a language? Um, and then sort of Chris, your question. I mean, I think it's pretty clear that images make things concise and make things clear and allow us to elevate our reasoning when we're using them in certain situations, right? Like I can show you an image of something like this diagram, for example. If I had to textually describe this diagram to you, it would be absolutely no use.
Mm-hmm.
But it just communicates so much so concisely. So it's pretty clear that images and visualness is useful. And I think the question is it useful in the context of programs? And it's tricky. I think it's clearly yes, because there are visual programming languages that people use in some domains. For example, music uses flow-based programming for their music setups, connecting filters, doing all sorts of crazy stuff. Like I think one of the examples is actually in the paper about that. But then it's more when you get to programming outside of a specific domain, it's more like programs, very abstract programs are visual notations useful there for you're writing just a generic, like for writing user interfaces, not for writing music software is it useful. And out of the problem, like I've got a friend who is a very knowledgeable developer, and he's like adamant visual languages will never be useful because they're sort of toys that once you get to a certain scale, you just can't fit it. You can't fit all the actors or all the states in the state chart into one screen, and then you sort of have to start internalizing the mental model anyway. And he thinks that text is actually a better way to go because at least it's more on the computer readable side, and then you still have to have that internal. So that's the area, and it comes other issues like unbounded. When you have a domain where you can have unbounded amount of actors spawning, then it gets really tricky. Like, how can your visual notation scale to that size? And that's something I'm not so sure about. Like, I think state charts are great because they're visual, but having said that, at work I don't really use the visual editor that much because I'm jumping around so many files. and I know how they work so well. I've actually got them into model in my head. I don't actually, and also the stately inspector. If you've got too many events coming, it just breaks. It can't handle the scale of our app. So even though I think it's like a great plus of having state chart, I just can't say that I really use it that much. Just a final point though on that. So I mentioned this to you last time, that we're very biased when we work on the same code a lot to think that code is all about, you've already got the mental model, so things that help you internalize the mental model aren't that useful. So, but I do find having a state chart inspector and visualizable really useful when I'm reading somebody else's thing that I've never seen before. It's just my job doesn't have a lot of that, but that is a very useful thing, and having code that is readable for other people, I think, is very important ability.
Yeah, I part of it is if you have a paradigm that might be susceptible to like a visual notation, you might not need the computer to generate that for you if you've been able to internalize it yourself. Like maybe that's a way that like a paradigm or like a type of notation can affect how you think about things, without needing the computer to be able to visualize it for you.
Um, I have a flurry of answers to things I've heard. One is, if you want to know what visual languages to create, just try to explain yourself to a CEO. And the first thing you do is go to a whiteboard and draw out to him. And so we're engineers, so we need the notation to contain enough detail that it can be mapped down to hardware. But the current thinking is that we need to do it all in one fell swoop. But you could do it in stages and layers and still get the same result using computer. Again, in 1950, it was unimaginable to waste computer time on stuff like this. But now we've got cheap computers, so we could invent a series of cascading notations that add more and more information as you go down from CEO lack of detail, 50,000-foot view of the way the product is supposed to work, down to production engineer wants to optimize it to sell a million versions of it, and reduce the cost by a penny per copy. You know, and so how do you get from there to here? And to me, that's the interesting part of, or has become the interesting part of programming is, so how do you fill that gap? What are the rules that say, how do you formalize what the CEO just said? And how do you continue formalizing it down to the point where you get enough detail to tell a stupid machine what to do? And
I really like I really like that framing of it, actually, what you just said. It's a really good way of putting it.
You have to write this down.
I've got it. I've got it. From boardroom to circuit.
One of the other perverse ways that I look at things is that software is just soft hardware. Whereas it appears that computer science has turned into a realm unto its own. It's a notation worship. It's software is a thing unto itself. Whereas to me, it's just a means to getting hardware without burning my fingers in the process, or more rapidly than I can solder things. And so when I look at the thing that that enabled this to happen, which was the invention of the CPU, which is really just a dumb little piece of electronics that, you hook up another dumb piece of electronics called RAM to it, and the thing will sequence its way through it in a very rigid manner, but it does something useful. And it has an API that you can program without using a soldering iron. And you can reprogram it without using a desoldering bulb to unplug components and replug new components.
Mm.
And we already had a notation that was referentially transparent called an IC, and we didn't need to force mathematics onto it. More papyrus-based mathematics onto it to make it referentially transparent. It already was. In electronics, there was something called pin for pin compatible. And early electronics, like when I built my first CPU, you built it with sockets. So you wouldn't have to solder it. You could just pull out the chip, put in another chip, and if you were like me, you did it because you blew them up, but you could also just plug in different manufacturers' versions of certain CPUs or certain logic gates or something, and they would internally work differently, and you never had to know why, because they were encased in epoxy, and it was basically build and forget from your point of view. From your point of view, you just don't care. I just use it. And we had, incoming tests that said, does this accomplish the very restricted set of outputs? Does it produce the restricted set of outputs given a restricted set of inputs? Everything else is undefined and I don't care about it. I don't need to be a completist. I don't need to know what happens in this illegal case. Um, uh, and, so the benefit of functional programming is, quote, referential transparency. And all the rules that lead up to functional programming say don't have side effects because they affect referential transparency. You can't unplug a function, plug in another one if the one you're unplugging had a side effect that changed something that you can't see. But the restriction in functional notation, because it was meant for writing down with a pen and paper, is that there's only one input and one output. And we immediately broke that restriction and added exceptions because we couldn't get anywhere without some sort of out. But that breaks, and I've only ever seen one truly functional program in my life, and it didn't come from McCarthy, and it didn't come from Simon Peyton Jones. It came from Justine Tunney, who wrote Sector Lisp. And she wrote a whole language that is 10 times smaller than any other language in existence that I know of. It's 436 bytes. The garbage collector is 40 bytes long because she stuck to the principles of functional programming and functional programming only. And when you do that, there's a whole pile of things you can throw away, which we have corrupted our programming basics by saying, well, we'll take functional programming, but we'll jam mutation into it. And now we're coming around 50 years later saying, but we shouldn't use mutation because it's bad. Well, yeah, we knew that already. Don't share memory. The original model was one CPU, one thread, and each CPU has its own memory and it can't share it because the wire is too thin to share a lot of memory. But originally, a CPU cost essentially $1 million, let's say. And so that model was too expensive and has dropped in price today to where, you can have a bowl full of CPUs, bowl full of actors, hardware actors, CPUs plus memory bolted onto them. And you can plug together an application. If you think like I do that software is just soft hardware, then taking a CPU, a hardware actor out of a bowl and sticking it into a design is natural. And I don't need to add 4 GB of software to make that work inefficiently, by the way. And I'm veering way off the
You know what's
track.
funny? There's actually a diagram in this paper that I think reflects Figure 4 that reflects exactly what you're saying here. Maybe not exact, but I think it represents it really good. I could let me send it in the chat, um, and I will. Yeah, let me do that.
One of the things I like about Harel's state charts is that they adhere to the principle of children can't affect the parent, whereas inheritance does allow that. And, so you can blow your own feet off if you don't program in a structured manner in object oriented. Whereas with a Harel diagram, you can't blow your feet off in that way because of that principle. So in some sense, what's needed in my mind is a discussion of the basic principles that we need to adhere to pick languages, to pick paradigms and concepts and other undefined things um, um, that would make our life easier. And we're picking and measuring things that are not making our life easier, but that are making the notation more thorough and so on. But it's in the end, a JavaScript programmer doesn't care if you tell him to use a monad because he doesn't know what a monad is. You didn't make his life easier by going down this avenue. And async.then stuff is just can be expressed more easily by just drawing two boxes on a whiteboard and saying there's a connection between them. This one runs first, this one runs second, and if you go like this, they both run at the same time. I can do that with two Arduinos, but in software, I need a PhD before I can say this.
Yeah, that's funny.
Yeah. Yeah. What do you think about that diagram, Chris, that you posted? I found it a bit of an interesting one. Because one of the parts of the paper is like just kind of just went onto this tangent for a little bit.
Okay, so conceptually, this concept of organized simplicity embodies like hardware. I feel like right, computers at the hardware level are like so dumb. It's wild, but that's what makes them us be able to do something with a rock, right? Like it's quite interesting, and there's probably exceptions to that now as hardware gets like more complicated. Um, to me, this concept of like computer programs, there's this chasm that we're trying to meet between simple programs and emergent behavior of systems is like really complicated, and so Fraser and I have talked about this before. It's the difference between uh, it's the difference between having a state chart and an actor system, right? Like the difference between synchronous concurrency and asynchronous concurrency. Uh, the latter creates this emergent behavior that you just can't predict, but it's also necessary to handle the complexity of the systems that we're making. And I really struggle bridging that gap or thinking about how we can bridge that gap. And this paper sort of articulates that perfect, which is like, how do we create organized systems that we can both understand, but also handle the complexity and randomness of the systems that we're trying to create. Um, and it feels like it feels like programming paradigms and concepts and whatever we're calling it help us with both of these paths at both sides of the chasm. Maybe I don't know. That's sort of what I was thinking.
One of the things I was inspired by is a master class I watched with Daniel Pink. He's a marketing guru, right? Not a computer science guru, but he gives a simple algorithm to determining this. He says just ask the question why 5 times. By the time you get to the fifth time, the answer is struggling and giving you so much detail as to what the problem really is. And so something you said earlier showed it out at me saying, why not just ask why? Why is this complicated? And, if you keep asking it and hammering at that question, you might come up with well, I also believe in brainstorming. So in brainstorming, you're allowed to be wrong. Um, but bouncing around the question of why, um, you might arrive at you might ferret out the nucleus of a problem. And once you understand the nucleus of a problem, you might see a better solution to it. And it may solve a bunch of other problems that have been stacked on top of the problem that are standing in the way of describing what the problem really is. And so,
yeah, a lot of that at the moment in software and especially some of the web development. So React comes to mind in terms of. I feel like they haven't asked themselves why 5 times when they're making React server components.
well,
So
the question why there is the first answer is because things are concurrent and concurrency is hard. The next question is why is concurrency hard? And it boils down to the kernel of the answer to that is because we allowed shared memory. And realistically, even in the 1950s, we knew shared memory wasn't a good idea. Don't do it. But they did it. And we ended up, crashing the Mars Pathfinder software on Mars. The hardware made it, the software crashed because of memory sharing. And the tower of complexity that arose out of allowing that. Sorry. And so you were going down the path of, web development is considered difficult because, like you said, no one has really asked the question why hard enough and enough times to get down to a reasonable answer. They're just adding band-aids to the problem.
yeah, and I mean, part of the motivation for me sort of diving into the synchronous languages was to really understand what people adjacent to the problem have been thinking about it. And related to what you said, Chris, I think the easiest framing of the problem is what the synchronous languages essentially compile to a single finite state machine. And they do that because they want to be able to do their formal verification methods on it. And so all of it is essentially the different synchronous languages signal a serial, basically a syntax sugar for generating a single finite state machine. You could sort of think about state charts like that as well. I know there's a little different with extended state, essentially generating infinite finite states, but it's essentially the same sort of idea. But as soon as you add the possibility of unbounded, unknown amount of finite states, and this happens a lot in web, not web, in user interfaces, I'd say, compared to say the hardware realm where you're almost simulating hardware, or you're bounded by the input output of hardware systems, which basically gives you finite states, whereas you can't spawn a sensor in an aircraft while you're flying midair. But with the way that we find the software interface, sorry.
Unfortunately, you can, but go on.
Okay. Maybe Boeing can. I don't know. But in a user interface, like the to-do list, you have a list of 0 to n elements, and so if you want to describe each item to do item as a with finite states, you can't now have a single finite state machine. So now you've just lost all your properties, the nice properties you have with a finite state machine, and that's like the inherent difficulty when you're dealing with collections and getting into that sort of complex. And yeah, the so then you're sort of like, well, how do I create a system where I can have this spawning nature but still understand what's going on? And this is something I think comes up a lot, and I've spoken to quite a few people who use state charts, come to this situation where it's like, okay, I can look at a state chart and I can understand what is happening in the state chart, but my system is a system of state charts, and a lot of the behavior of the system is determined by the interactions between the state charts. And if you describe it in an actor system, which is very, very unstructured, you basically the way to work out how what's going to happen is to simulate it and just run through it and see what's going to happen. And so then you wonder, well, how much is understanding the part that makes up the whole? How much does that contribute to understanding the behavior of the whole? And I think that's like a really interesting question that notations might be able to help us bridge that a little bit, where maybe you provide semi-structured, instead of having actors that can talk to anything and do anything, maybe you can describe boundaries to how the actors can communicate, where there's event interfaces where you're only going to get these events coming in, and you know that you can connect that to another actor which can only receive those events, and start sort of creating a semi-structured aspect to the system where you can still have some of the more degrees of freedom, but not unlimited degrees of freedom. But it's a tricky one, and I think a lot of what we're talking about is really bridging it. It's about bridging gaps, and what I noticed in both these papers actually that we've read is that they seem to want to bridge the gap in one language. Like Van Roy was talking about, the ideal language. If you look at all like 4 languages that have done really well, what are their common aspects? And then the mathematical one was sort of like, what if we could make maths a programming language, essentially? And I think what Chris and I have been thinking about, and maybe Paul, what you talked about, like a cascading layers, is more about like bridging the gap not in one go and with one language, but like little languages that can compose, and one deals with the high level, one deals, and I actually think Harel was getting to this with not just state charts, but with live sequence charts. I don't know if you've come across those, Paul, but they're essentially like a very high level. Sorry?
I haven't studied them, but I know of them.
Yeah. And they're essentially like a very high level description of what so a sequence would start with a user or external input, which essentially an event, and then you chart it through the high level modules you have in the system. It could be like light on, and then there's light, and then something else. And it's just a very high level description. And then Harel's envisions this sort of refinement where you can then fill in the details of the module using state charts, actually implement this logic, but you still have this high level description that serves to not just as a aid, but also you can actually verify the layer underneath using that high level description, so that it's involved still in the program, not just an architecture diagram left to the side. And I always found that very, very fascinating idea. I think one of the big question is also is how do you the links between the layers becomes very difficult because you start having to maintain maps between identities of things in different levels of description. Like I've got this thing here that should relate to this thing at this deeper notation, and in having to maintain those relationships or just describe them can be difficult. And yeah, so there's definitely a lot of challenges there. But so I've spoken a lot, so happy to hear thoughts on that.
Um, the difficult part is what researchers get paid for. They're supposed to think about hard things and then understand them and then explain them in a simple way. And what we've got now is they understand them, but they don't explain them in a simple way. Um, in essence, what I strongly agree with what you said. And the word layer makes a lot of makes is a loaded word that makes a lot of sense to me. And I think one kind of layering that we don't consider enough is syntactic layering. So, if you just, one of the things I'm getting at with the little languages for machines is that you can then specify a little language that a parser can parse and declare that's okay or that's not okay. And hence you can then define little layers of things. You can define things in layers. At the moment, we've got one layer, and that's all, basically one layering mechanism. That's a lambda. If you've got a lambda with one parameter, curried out of its brains, then that's the only thing we've got. And I went through a reading group on the AGDA uh, Foundations of Programming Languages in AGDA book, and what screamed out at me was that they were using lambdas all over the place to try and abstract away, or what I call a simplifying assumption. So they're trying to make simplifying assumptions, but describing them in the same language of lambdas and little bits of syntax that I fundamentally found obscured what they were trying to get at. And their penchant for taking descriptive names and compressing them down into a single Greek letter didn't help much. That's one thing Lispers are accused of. They use names that are way too long because, unlike underscore, they're allowed to use dashes in names. And so you can write a whole sentence as a variable name. And, that's an attempt at human readability of the architecture. But it has its own drawbacks in that it just looks too fat. It's too busy. And like what you were saying, Fraser, is you want to start at a 50,000 foot level. You want to get a quick overview of what's going on, and whatever interests you, you want to dive down that thing and get another medium level overview, and then dive down maybe that and get a more detailed overview. Whereas we're forced now to, explain on a whiteboard what's going on and then dive right into lambda notation or programming notation. And we found a myriad ways to abuse programming notation. McCarthy originally wanted cont to mean a conditional function evaluation, and we have twisted it to mean a conditional control flow evaluation using variables, which obscures what's going on in a big way. And therefore, if then else, I tend to think if then else should be discarded from programming languages. And that may be another reason I like Harel's notation, is that control flow is very obvious. in the diagram. Um, Another belief that I have is that we know how to write equations, and we shouldn't stop writing them that way in text. We shouldn't use visual languages to rewrite textual, the things that text does well. It's, in my mind, it's silly to write an A plus B box because we already know how to concisely write A plus B.
Yeah, a visual. That's what I was thinking. It's syntactically more concise to
Yeah,
represent that textually, and it doesn't have to like. I do like I feel like when people talk about visual programming languages, they're like looking for this one visual programming language
yeah,
to rule them all, and it's like it doesn't have to be like that, and that's why I really like these framings around paradigms and notations because it's like things can be expressed differently, and and that's okay. Uh, and we should figure out what is good at being expressed at what level and in what ways,
yeah.
and it seems like the cusp that we're at now is we're trying to build these general purpose programming languages to define all these higher level architectures and data flows and reactive behavior, and it's like maybe there's other ways to express that better that we can't because we're trapped in these general purpose textual based programming languages.
Right.
But yeah, that doesn't mean that 1+1 isn't best expressed in text.
Yeah, exactly. I also strongly believe that a specific purpose language is better than a general purpose language.
Mm.
And because we've been brain locked into thinking we need to use GPLs, we don't think about SPLs very much. We've created this thing called DSLs, but that's a loaded word, and DSLs now are really GPLs. They're so complicated that they're hard to understand what you really are doing there. They they present a quote higher level concept, but with so much detail that you know it really doesn't matter. It didn't help.
Yep.
It didn't help me think through the problem better, easier, faster.
Yeah, that's why I use the term little language now because DSL is everything and nothing. It's become meaningless, and it's like there
Yeah,
is these small languages that maybe they embody a paradigm, maybe they embody a domain specific thing. Like I do think there's a distinction between that, but um, they're little and they're extensible. Like there are specific, they're intentionally powerful because they don't describe everything, and there's specific extensibility mechanisms built into them that allow them to stay small while being used in a wide variety of programming or computational environments or use cases, for example.
right. So my own questioning of myself as to why don't we use more languages instead of a general purpose language? And the answer I come to is because we haven't figured out how to bolt little languages together to form a larger whole. And that saying it that way makes it obvious what we need to do. We need to find a way to bolt little languages together to make a larger whole
Yep.
instead of forcing a zillion paradigms into a single language.
Yep.
And Van Roy is saying the same thing. He's got it down to two paradigms in a single language. I, I think a single paradigm in a programming language is the right way to go. Like I would use Prolog if I wanted to search a fact base, but I would rather use JavaScript if all I wanted to do was format a string.
Yeah.
The, but the Prolog guys have gone and forced a way of formatting strings in Prolog Think that makes it harder to think about how to format a string.
Yep.
And um, and one of the little experiments that I did in probably in between aerograms and one of the other variants of what I'm doing is that I created a little language. Because I had OMJS, I could whip off the language very quickly. And because I had my own DSL for not writing the JavaScript that goes along with OMJS, I could whip off a whole little language very quickly. And the little language basically created 3 other programs. It created a program in Prolog, a program in JavaScript, and a program in Bash. And it joined them all together. And invisible to me, it just ran the thing and produced a result that I wanted. And so that was one way to bolt little languages together at a syntactic level. So I created a new syntax that said, I want to search this fact base for these particular facts. And that's all I want to do. I don't want to do all the other stuff that Prolog does. And when I get a result, I just want to print another string. And so that was Prolog and JavaScript. And then I pooped out some bash that said, so run these 2 programs and pipe them at each other. And it worked. Until it didn't work, and then it became a pain in the butt to debug. But the principle was there, and just thinking that way caused me to think of other things that again aren't classified by Van Roy as paradigms, but there's something more than type checking that you can do to a project. There's what in electronics design, there's something called design rules that say, for this particular project, make sure that this doesn't happen or does happen. But it doesn't apply to every other project. It applies to that one project. Well, if I'm allowed to knock that off quickly, then I have no qualms about saying it several times or characterizing my project that way instead of generalizing it to preconditions and postconditions and stuff like that. I just have a little script that says, just make sure this is true. I'm wondering, are we running out of time, or I don't know how long this is supposed to last. I'm rambling away.
Oh no, I'm good on time. Personally,
I probably will shoot off pretty soon. But of course, you guys are most welcome to keep chatting. Yeah, I think it's been really good. Like, I've taken 3 notes. I think sort of sums up like extended discussions, not so much related to the papers, but sort of the notion of cascading layers, trapped in general purpose programming languages, and then thinking about how to bolt the languages together. I think it's really the essence of some of the things we've been talking about. I mean, as an example of the challenge, so one of the things I've been thinking about is I really like state charts, but I have come to think that there may be not, there's an impedance mismatch with describing user interface with state charts, and I've talked about some of the reasons. I feel like the components themselves are useful. Finite states are useful for a way of describing the current behavioral configuration of the program. I think extended state is obviously very useful. And I think events, the event interface, there's something just really powerful about the actor model where you just event in, event out, and less of a dependency on the call and return. The passing of control flow is that difference between calling a method on an object versus sending an event. I think that's very powerful. And so I've been playing around with so many different configurations of this, even to the point of thinking, well, could you have events coming into some sort of container that outputs nothing but descriptions of what actions should occur? Essentially, if I have this event, what should I do? But do nothing. So there's no side effects. There's no state assignments. There's no actions being fired within this little processor, this reactive processor, and then all of that is handled maybe by different notations. Maybe you have a notation that can handle, or at least a module that can handle actions, and maybe that can be broken down into different types of actions being handled together. And maybe the assignments can be handled specifically by a database layer or something specific to that, rather than it all being embedded in the state chart notation. Because one of the issues, I think, state charts themselves suffer, I think, from this idea of an overloaded notation where they make finite states really prominent and easy to express. They make the flow of events through things and they're not expressed very well, or not. I feel like another notation could do that better. But you do run into this problem where, say, you have a module that processes actions and uses maybe finite states to determine what actions should be applied, and sorry, it doesn't process them, but determines action descriptions. And another module that needs to process the actions and actually fire them. Sometimes you actually almost implicitly recreate the same hierarchy of states that you had over here to do the same thing. You see it in sort of the component when you describe a UI with a state chart. You almost have to implicitly recreate the state chart to create a component tree that visualizes the states of the state chart. So you end up with this duplication that is also not very nice and feels like implicit or even explicit coupling between them. I think that's a big challenge of having little languages, is really dealing with the how you're referencing between something and also not repeating yourself. Ideally, you want to be adding, but not duplicating between these layers of description, and it can be. I think that's a big challenge.
I don't think it's a very big challenge because the build and forget mentality says, I don't care what you do in there. I'm just going to send you some events, and whether or not you duplicate my states, I don't care. As long as I can send you some events. Another thing that I was going to comment on, I think state charts are great for expressing control flow, but I'd rather use an object-oriented language for describing data structures. And I'd rather have a language that said, I can't express the construction of that data while I'm also expressing control flow. So I'm not sure if that made sense. One of the things that you see in assembler, and one of the very successful strategies I saw in building compilers and was used in the GNU-C, was the idea of separating control flow from data construction. So you had operators and operands. And a paper that I found to be very influential in my thinking was orthogonal code generation. So you generate code in two passes. You generate dumb code, and this is what GCC does. It generates code for a fake machine that has an infinite number of registers. They all start with the letter R. And so you can go from R0 through R99 through R199, R299, just depending on how much program you've got that you need to express. And then you apply what in GCC does is a small peephole analyzer that runs a little window through and says, oh, there's 3 of these instructions in a row. I'll just replace them with this one instruction. Because I know this is a particular ARM processor, and I know it can do this kind of thing. So winding back to So I don't think that it's actually that hard. I don't think it's actually a difficult problem, or I know it's not an insurmountable problem. And that to me means difficult or not difficult. If I know how to do it, I don't think it's difficult, even though it may take a lot of time.
Mm.
But if I'm allowed to declare a small syntax, which is in essence a, a structured API to something, and if that's the only thing I'm given to this component, if that's the only way I see this component, then I don't care what's inside of it. Is it structured? Is it functional? Is it spaghetti code? I just don't care as long as it works. And that's what we've got in electronics. We've got a bunch of spaghetti code, and it's epoxied out of our way. We don't have to see it. I'm running over your time, um, but so I guess I'm trying to say that what you said I agree with, and um, I think you need to explore what little languages, machine readable, what little languages can do to make that problem more solvable than you tend than you seem to say when you were saying. And I'm looking at you, Fraser. Sorry, I know who I'm looking at. um,
Yeah. So I think I just think you've given me some food for thought there. Um, definitely. Yeah, I think I'm trying to think. I think we use at work actually. We have some sort of calculation builder functionality. So we've used that to define recursive grammars and things like that. Really cool. Definitely like an area like the parsing, compiling side of software is not so much strength of mine. So it's definitely something I need to explore. And yeah, I'm sort of conscious of a lot of that where like there's a lot of silos of useful information, reactive systems and synchronous languages being one sort of silo. And I think what you're talking about is almost like another area. Obviously, compiling is a very fundamental part of computer science, but it's like what I'm trying to do is really draw upon a lot of what other people have done, so I don't have to do the work myself. But also, yeah, like it just makes sense to reuse the good thinking and the ideas of other people, but actually just finding coming across these silos can be. It takes something like you, Paul, to say, "Oh, Fraser, have you thought about this?" To actually get that jump across.
Mm.
And so part of like what I'm hoping to do with this group and also my own research is to create pull together the bits of information. So the actual research, just researching the research, is like something I've been doing that I really enjoy. So often I'll come across something I'm like, wow, this is like really relevant to my area, and I don't think a lot of people have read this. Yeah, I have that thought a lot. So I'm always happy to be told there's this another area that could be useful because it's just so valuable to then be able to jump into this other area. And yeah, it's just great to cross pollinate essentially. Um, I think yeah, it's quite easy. It feels like software moves so fast, and it's quite easy to forget the great body of work that has happened. Um, yeah, it's and then the other thing that I've been thinking about just before I go is like one thing that's really frustrating is the lack of examples when people talk about things. This happens a lot in web development where there's a new framework. It's like, oh, here's our framework, it's great. And then they make a to-do list. It's like, okay, I'm not building a to-do list. How do I know that what you've made is going to be in use to me? It's sort of like, well, Facebook uses it and it can make a to-do list. And it's like, well, okay, I'd really love it's and even when I describe my own things, like I've talked to Chris about event charts, I've struggled to actually what sort of how do you condense it? The complexities of a program into something that you can precisely write and then say, okay, like this is something that my notation actually works for. We're lacking the sort of canonical examples or the taxonomy of applications, and it's something I'd love to create. Is sort of like you see these sort of movie apps, right? It's like, oh, have you written this movie app? This is like how you show that your web framework is any good. It's like, well, by adding, maybe you've got 100 pages, but is really adding one more page to a web app any more proof that it works than having 2 pages? What have you added there? But maybe if you added a WebSocket connection, or maybe if you added some other bit of complexity, you're now expressing a different type of application. So it sort of gets into this idea of like, what are the paradigms and concepts of programming language, but then that same idea applied to like applications and the problem domain. So that's something I'm working on, but at the same time, I'd love for there to be like a list of 100 examples. It's really tedious making examples because it's so hard to. I know that when I build my application at work, that there's tons of things that seem to be okay. This would be a great example, but when I pull it on its own, it's almost not. It's missing the context, and it's missing other pieces that made it really complex, and now it just looks really simple. So it's like, how do I contain and really pare down something? An example needs to be concise, and it needs to be, you can't ask people to make an application that's 10,000 lines of code as a something necessarily. That's not throwing the baby out with the bathwater. This is a hard challenge of making an example. So it's a long process.
Yeah. No, thanks for sharing. Yeah, it's hard. It's hard to articulate things. It's hard to find simple but evocative like examples of like, oh, where would this be useful? And I think the same applies to what we talked about today, like with paradigms. Like okay, let's say we have a toolbox of paradigms and we can compose little languages together and create these beautiful stratified layers of all these things. It's like, when do you use what, and how do you know? I think that's the hard thing. It's like, oh, this paradigm is best for, so sometimes like a paradigm isn't best for like a specific domain, like music. It can be a little more abstract than that, and I think even if we had like capabilities to sort of swap these little languages out and the accompanying paradigms, it's like, when do you stack them this way and when do you stack them this way? Those are really hard answers to know. So I think it's just very similar to what you're saying too.
That's really just, the mark of a good architect. Someone who's done it, who's made mistakes and has learned, let's do it this way.
Yeah.
Because it'll work. And so maybe that's what I'm getting at is, we need a language for architects. People who just want to glue little Lego blocks together and make things work, and then hand it off to engineering teams that will make it work better and faster and cheaper and whatever else. And what we don't have at the moment are programming languages that really help you architect by snapping things together.
Yeah.
But to me, that's what little languages means. That's what paradigms mean, and so on. It's all sort of floating around there. But we're finally getting enough tools together that we can start thinking more this way than we have been.
Awesome. Well, I'm excited for us to continue talking more about this and exploring more. I'll stop the recording now.